Okay everyone, in this video I'm going to try to explain why the Harrier is so super difficult to build. As you all know, I've been working on the Harrier project in the background for many years, and I'm going to reveal you in this video why it's so difficult. So, to give you a short understanding, I'm going to divide my story into three different storylines. First is hover. Secondly, of course, flying, why the Harrier is so super difficult to fly. And we're going to talk about transition. So, and I'm reading all your comments, and of course all those hover looks the same, but it comes with a story. So lean back, take a coffee and enjoy this video. Okay guys, it's going to be more interesting because we're going to talk about thrust to weight ratio, and I wrote down the numbers so I won't forget you the important numbers that you should know and to understand why hover is extremely super difficult in RC world. So in our experience, and we did a lot of hovers, our thrust to weight ratio is 1.5 to 1. And why 1 to 5 or a higher number? Because we need escaping ground effect. So we need more power to escape ground effect. And we need acceleration during vertical climb. In this case, our model is 7 kilos. If you divide it by 1.5, we will reach a total thrust of 10.5 kilos. Well, that's easy with a really big Stobl, right? But in our case, we are dividing air because I like to go scale. We're going to divide the air to 4 air outlets, and we're going to do for each outlet a 2 times 90-degree angle turn. This will result in losses. As you all guys all know, I've been printing, redesigning Pegasus modules since 2017. And we win also the Oogkunde for the WM vertical takeoff. So, and we went second place there. So this was 2017. From this event, we've gathered all our bright minds together. My friend Andrea Schiek, René Rosenträger, Alois Wessler, all these wonderful minds we've gathered, we've designed, and our best optimum flow is 70% out of this Pegasus module. Of course, you can squeeze more the outlets to get it to reach a higher airflow, but it will result that the motor could burn. And again, this is not so funny because you want to stay in the air for at least like 2 to 3 minutes, if it's possible. So 0.7 is our most optimum efficiency. So with this number of 10.5 kilos, we have to multiply it again by 1.3, and it will result in 13.65 kilos. So let's say 13.5 kilos we need from this big main EDF. It's a lot, and we need this number to escape ground effect, and we need acceleration. So we are talking about for a 7 kilo models. For a 7 kilo model like this one, we need 13.5 kilos to take off vertically, and to get acceleration during vertical climb and escaping ground effect. Now, if you look into the datasheet of the Stobl, we used the best 128 Stobl there is, and this can provide us 12 kilos at 50 volts according to the datasheet. So we are still short on 1.5 kilos to escape ground effect again. So this is the reason why I use this additional EDFs for pitching, rolling, and this will provide me this extra 1.5 kilos, which I actually don't like because I want to get so scaled as possible. Understand? So what we decided in this group of really nice friends and really bright and smart people is that we call this number for vertical takeoff T factor. This is also applicable on my F-35B project. And this is the number with all the EDS what you're using. It's a plus number altogether. This is our total of T factor. So thrust to weight ratio, 1.5. And if you can do 2 to 1, and this will relax the setup more. So how higher the thrust to weight ratio number, how more you can extend your hover time, or you can choose to add some skill features like a retractable landing gear, more integrity to the fuselage to make it a really beautiful plane. But this number is really important because you cannot save on weight of batteries, you cannot make the EDF smaller, the weight of the cables you cannot cut. It's really extremely difficult to make it lightweight as possible. But 7 kilos, it needs a really good fuselage. So I'm reading your comments. Well, Joel, it looks all the same. Why not using a bigger LiPo? So for example, in our video, what we've done in the Munich, we have been using those STOVL LiPo shops, 4500s, and these are 65 Cs. So they are really, really powerful. So this number together is like 1300 grams. This is including the 7 kilos. But I fully agree with you that we should use 7000s. But these are 1.65 kilos. So if you calculate this again, this model should weight, I've wrote it down, guys. So this model should weight not 7 kilos, but 7.43 kilos. If you do the math again, we will reach a thrust to weight ratio. And this number is 14.3 kilos. And again, this is a 6S setup. And together with the Schubler, we were reaching 12 kilos. So this is, so we are still 2 kilos short. And as a result, yeah, including with those additional EDFs, we are not able to take off vertically from clear ground. Of course, now it comes, you can use bigger EDFs, additional EDFs. But again, fill in that number, bigger EDFs, more weight, they need a bigger LiPo. So this is kind of a closed loop discussion, what we always have. But we're pretty damn close, are we? So I hope that you are guys still with me. I know it's a little bit of boring explanation, but yeah, I find it really important that I explain you guys why all this hover, also with this smaller Sea Harrier, why it's so super difficult. Hover is really difficult, guys. And of course we can add bigger propeller drone-like setup in the wings. Of course, then we will finish together. But for me, it's really a hobby, and I love doing this. And so our Sea Harrier is a semi-scale model. This is a project from René and Andrea Ziek. They have a different approach, and we all have our approaches. We combine our ideas to get the best of the best. But believe me, guys, hover is not actually the most difficult thing of the Harrier. So let's go into flying the model. And then after this flying section, I will explain you the transition, which is even more difficult because we're going to tilt the nozzles evenly, so you lose thrust, right? So you can think about it during the next topic, flying the model. What could be happen then? So let's jump into the flying part of the Harrier. Okay guys, why not explaining the model as you see it? So if you see about flying the Harrier, of course CG is quite easy to find. And we are flying this model already really beautiful, with thanks of my friend from Switzerland, Beat, who is already flying and the prototype version of this design. So if you look to the Harrier, we got a down sweep angle, we got a back sweep angle like all jet fighters. So what will happen? And we got pretty small ailerons. And during slow speeds, these guys won't do any good. So the real Harrier is using a valve system, in my case an EDF, which is connected with the aileron. So, and this is pressurized by the Pegasus engine by bleed air. So when the pilot chooses to roll to the left side, it will push his airstream downwards, and from the other side it will push his airstream upwards. In this case, you will be able to fly low speeds with great control on the roll. So in our next, before we go actually to our flying attempt, I would like to add the same trick, but we're going to do a different design in our next video. So make sure to subscribe and put on the notification bell if you won't miss any video. I'm going to remove these EDFs and we're going to take bleed air from the main motor, going into the pipe into the wing, and we're going to do the same trick just to be safe for our first flight. If you go with this steep angle down sweep and back sweep design like the original model. And guys, we can go for a semi-scale wing, make it a less angle, but this is how the Harrier looks like. And this is no discussion that I'm going to change the design as it is. This is how it looks like according to the designs. I'm not going to change that. So this is about the wing. It got a nice lifting profile and it flies really good according to my friend Beat in Switzerland, and I've shown you guys the video clip. Our next topic is the tail. We got a quite small vertical stabilizer. Well, the wheel Harrier got also bleed air in the tail for yaw momentum. So what I'm going to do, I'm going to add a small EDF. I'm going to do a small valve system. I got it somewhere, by the way. Here it is. So this is our old design from 2018. This is for yaw and this is for pitch. This works actually. And in this case I'm going only to use the yaw momentum valve. And for pitching we're going to use some bigger EDF to compensate the T factor. So like I told you in our hover section, I'm going to remove these EDFs. Going to take some bleed air from the main engine, so I will lose some thrust from the Pegasus, and I will lose the T factor from these small EDS, and we're talking about 300 grams, 200 grams each for T factor. So I'm going to increase the EDF in the front and in the tail. So these are 50s. I'm going to push them up to 65 or maybe 70 millimeter to compensate the loss of T factor. On the other side, I will get rid of the weight of the EDF. I will get rid of the weight of the cables, the ESCs, and I don't need to give them juice from the LiPo. So in that case, I will lose weight as well. So maybe this could be a win-win situation. Let me know in the comment what you think about this idea. Well, I never talked this much, but I need another coffee. So if you're still with me, we're going to the transition part. Transition with the Harrier is a bit more easier compared to the F-35 because we got one main engine. What the Harrier does is just tilting the nozzles. We got some nozzles over here. So we are in hover mode, like this. 70% efficiency, we're pushing. And then we're going to tilt the nozzles back forward, or for a forward momentum, to create a forward momentum. So if you look at the lines, 90 degrees downwards is the ideal setup. And now we're going to split the air to the back. And it's already pushing maximum thrust. So it will result in a whoop, it will drop down. This discussion is still ongoing, so we can do it really quickly. We can climb really high, but if you climb high, yeah, if you reach like 30 meters of height, then the battery is already dead empty, and we got like 1.5 minutes, 2 minutes with this battery. So this is a choice. So in my case, I'm going to focus on normal takeoff, fly a few circuits like the F-35, like we did, and do a vertical landing. With this kind of LiPos in 2025, I think this is the best way to have fun with the Harrier model. Yes, we can do a vertical takeoff outbound, but the battery will be dead empty. So guys, let me think about your ideas, what you think about my idea or my approach. So this story what I'm telling you guys has nothing to do with the flight controller. I'm still using the KK2 board. And I met some really wonderful guys at the STOVL event in Munich, which are flying with an INAV system, which I really love. So this is going to be the new topic from now on. Changing the flight computer and building a new Harrier. So guys, let me know your thoughts. I'm really curious what you think about this idea. There are already many wonderful builders like you watching my videos trying to build a Harrier as well. There are a lot of passionate guys like you and me who are trying and willing to build the Harrier as close to scale as possible. But I also hope that I explain you enough of ideas, my approach from the last decade, how I approach the Harrier, how to solve it on my way. And there are more ways to Rome, they say it in Dutch. But everybody got his own approach and I respect them all. So show me or give me your thoughts in the comments. And we didn't even talk efficiency about the motor. This is the reason why, let me show you. This is the reason why I like the JPs. The gap between the blade and the stator housing is super narrow. So we're talking about a really high efficiency motor, but the biggest JP is a 120 like this one. Schubler they got really big motors, but it's actually too big for this model, 1:8, 1:7 size. And Tom, we met on in Munich at the STOVL event. I'm looking really forward to your results. So I've met Tom on the STOVL event. We were talking and discussing to integrate this EDF into the Pegasus module. Can you imagine? And this is a really wonderful idea. So we are going to shorten the length of the Pegasus. So we've got more space in the front. And then we can have a really smooth air inflow. We're talking just about T-factor this whole YouTube video. But yeah, we got also some pressure in the front because this motor needs to breathe. So if we can create more space in the front, we can reduce the weight of the motor. We can reduce the weight of the Pegasus module, which is now 2.2 kilos together, by the way. Yeah, then we are getting somewhere, right? So we need to get the thrust to weight number right. The T-factor must be good. If we can get it underneath the 10 kilos, it will result in a really long hover. So guys, I think this is a nice moment to end this video. I hope you appreciated that I'm willing to share you and reveal you my ideas and my numbers, what I think, how to build a successful Harrier. I know it costs a lot of time to build a really cool Harrier, and I'm really thankful to ColorFab, which allows me, and I've learned from the guys how to print the models really fast and rapidly. And yeah, all my sponsors, a shout out, Charge Servo, PCBWay, ColorFab, JP Hobby of course, and all those others. Thank you so much for helping me and guiding me to get the best of the best to make this project a success. Guys, thank you all for watching. Make sure to hit that subscribe button. If you didn't, also turn on that notification bell, because we're going to focus a little bit more on the Harrier for the next few months. We got also the X32, so we're going to do a lot of fun. Okay guys, see you in the next one. Ciao.